About 2 years ago, I created a reverb VST plugin in C++ and JUCE, basing the algorithm after a proposed idea and writing it completely from scratch. I then wrote a whole script for a video, got a voice actor and everything, did some storyboards, and then never made the video. Why? Because I'm the best YouTuber in the world, I know. But as the current project I'm working on is taking a bit longer than expected, and I need a bit more time to get it done, and arguably I may do other projects to build a better foundation to that project since I did bite off a little bit more than I can chew, I thought now's the best time to officially add this plugin to my portfolio and officially name it the second project on the road to Focusrite. Oh yeah, I'm also doing a solo talk at the Audio Developer Conference now. Reverb can be defined as sound waves traveling through air and being reflected back, usually from the perception of a listening source. If the reflections take too long, we perceive them as an echo, but if they come back fast enough, they meld together and make a spacious kind of sound. That sound being an indicator of the current location, the materials of the surrounding enclosures, and the space the location occupies. This spacious sound describing all of this being reverb. I am oversimplifying a little bit, but it is the general idea. With this definition, it's safe to say that reverb really is just a series of really fast echoes, some traveling at different rates while cancelling out other frequencies depending on reflection surfaces, factors related to the listener, and other physical phenomena. I talk in my sound design video on the many different methods that have been utilized to replicate the sound, with one of the most common in the software world being convolution reverb. And as cool as convolution reverb is, it is kind of hard to get up and running, especially with all the math. And so as an easier algorithm to break into a reverb design, I decided to pick the one proposed at the Audio Developer Conference back in 2021 by Signalsmith Audio, which is the design that we're going to use today. The basic structure of it follows the idea I presented earlier, reverb just being a barrage of reflected sound waves or really fast echoes. These echoes are also modulated and have lower and or higher frequency contents, as some frequencies from the reflected sound waves take longer to get back to the listener, while others are lost entirely. To build it up the same way the talk does, the first thing we need is a delay. In software, a delay is achieved by the use of a circular buffer. We have a buffer that holds a read and a write pointer. When audio hits the plugin, we halve the energy of the sample at the read pointer and add it to the incoming sample. We then both write the sample to wherever the write head is and also send that sample to the audio output. Afterwards, we increment both the read and the write head by one sample. It's called a circular buffer because when any of the pointers reach the end of the buffer, they circle right back to the start. We also zero out the buffer first, so we're not reading any illegal data. The consequence of this setup is that the read pointer eventually gets the samples that were written a while ago and are added to the incoming sample, even if that incoming sample is now theoretically zero, or there's no audio coming in. So we end up repeating what was previously inputted a while ago in our output, and we end up with a delay/echo that slowly fades away the more we halve, which is pretty neat. This actually isn't that hard to write in code, and even though my code gets a bit more complicated, it's easy to replicate this behavior via this video from the audio programmer. There's still a delay/echo though. To get a reverb sound, we need to mangle these echoes and make them repeat fast enough so that it sounds more diffused. If we had multiple channels, each of them having delays that vary in length, for simplicity, imagine each channel has a slightly longer delay time. The sound gets more complicated and these echoes sound less distinct or separate because there's, well, way more of them. To have this vary in delay time, we simply just have a different separation sample number between the read and write pointers. This separation specifies how long the delay would be. And so yes, because we now have more channels, we also need a circular buffer for each channel. If we had 8 channels of delay/echoes, we need 8 circular buffers, which does sound like a lot of memory, but you also do have a choice of how big you want the buffer to be in the first place. We're gonna use 2 times the sampling rate as the size of our circular buffer for each channel. That way we always have 2 seconds of data just in the buffer because, you know, the sample rate is 1 second, 2 times sample rate, you get it. On that note of adding more samples, it doesn't really seem that practical to just add on more buffers until we get enough echoes that smear together. We do eventually reach an unnecessary amount of memory usage at some point. So instead, we can make more smears by just mapping each delay onto all the other channels. The complexities and smear compounds, as now each delay from each channel gets mapped onto all the channels before it gets delayed again. The circular buffer imagery has worked up until now, but I think delay line imagery is actually a little bit better for this concept to be understood. When we first get our batch of audio, we have an echo that gets delayed by increasingly longer times throughout the channels. Each sample from the different channels or lines gets halved in energy and are finally mapped onto every channel before going back into the delay input. And on the delayed input, each channel then once again get delayed by increasingly longer times. So we're separating the delays of the previously combined audio across all the different channels as they have different delay times. You can rewatch this little explanation again so it sinks in, but based on how complicated it sounds already, it may seem apparent that the sound has also gotten a lot more complicated. Signalsmith actually used a test click sound to see what the sound sounds like after each step to see how it progresses. So this is what a tick sounds like after the initial delay or echo. This is what the tick sounds like after having multiple delays for each channel. And here's what the tick sounds like after having multiple channels of delays and mixing them together. We're ever so close to reaching that reverb sound, but we need just a little bit more of a diffuse sound to really sweeten the deal. Which then brings us to the next section, the diffuser. The diffuser is going to be placed before the multi-channel delays, which I'll call the technical term feedback delayed network, or FDN. The feedback part being indicative of how the echoes are fed back into the input before it's sent to the circular buffer and output. And well, there's a network of lines, that part is pretty straightforward. But even though the diffuser happens before this network, going over this network lays the groundwork for the diffuser. The input of the diffuser is also multi-channel, so we do the necessary mappings if need be to start off with. The mappings being making every channel the same bit of audio if our input is mono, or having 4 copies of our input if we're in stereo. Either way, we're gonna have 8 channels as our example for now. You can push it to 16 channels if you really want to, but there's always trade-offs. This is software engineering after all. But we're using 8 channels for this example. I should say that even though we are actually going to be using 8 channels for this example, and that's what is built into the code, and that's going to be what the final output is going to be, I'm using 4 channels as a showcase because having 8 lines in the illustration would be pretty compact and would be pretty ugly, so I'm just using 4 channels to just make everything look a bit clearer. But in general, there's 8 channels. If you want, think about it as all the 4 channels are actually going to be duplicated. Think of it like that. But yeah, there's 4 channels there for illustration purposes, but we're actually going to be using 8 channels, okay? I hope I'm not talking too fast. This is my normal talking speed. Okay. And while we're not on the feedback delay section anymore, the diffuser actually does a lot of the same tricks. We first delay the incoming sound from each channel by different delay times, then shuffle the samples around and switch the polarities to add some randomness. Finally, sending everything to a Hadamard mixing matrix. And I should probably actually mention these matrices now too. So this design, despite conceptually being hailed as a simple solution to a complex problem, is still kind of complex. I don't mean that in shade to Garion. I'll actually get to that in a minute. He's actually a really, really cool guy, but for a beginner, it is still pretty complex. I wouldn't be the first to admit that, well, I don't really know what a Hadamard mixing matrix is. Furthermore, the mixing that we did previously for the feedback delay network, which is, the mixing that causes all the channels to have the same audio before going back into the input, is called a householder matrix. I'm not a math expert, and arguably Mr. Love himself, having a degree in mathematics, he is. That's why while I was implementing this algorithm, he himself was actually a really big help in the audio programmer Discord server, which goes to show that this community of audio programmers, while being so close-knit, it is expanding a bit now, but still is a little bit niche. People will always extend a hand, which you don't really get in a lot of different places. And to kind of zoom in on this message, it is definitely possible to implement the matrices without a big knowledge on what they do. Don't get me wrong, I was able to do it, and by the end of this video, you'll figure out how I was able to do it as well. So it is possible, but it would just be nice to know, to understand what the whole algorithm does in totality. You know what I mean? This is more so what the section is about. I'm breaking a bit of continuity here in my explanation, I know, but the question of well, what's a Hadamard matrix may inevitably be asked, and I'm really not the best person to answer that question. Maybe someday, but just not today. That Hadamard mixing matrix, however, is the final piece of our diffuser puzzle. Pretty similar to our feedback delay network, just minus the feedback. Our delays for each channel are also a lot shorter compared to the feedback delay network, or FDN, I'm gonna call it that actually, to the point where the lowest delay for some of them can actually be no delay at all. And our diffuser works in a way where if we want a more diffused sound, in this application, we really can just add more of them. Adding on more diffusion steps doesn't use any more memory, since everything is still being handled on the 8 channels in terms of circular buffers for the delays, and the computation time will take a bit longer, but can still be written in a way that keeps our plugin real-time safe for audio. However many we use, we stick that onto our FDN, which is already expecting the 8 channel input, and well, that's our reverb plugin. The full step process is this: map or split or duplicate our audio the way we see fit on input to match the number of channels we're going to be using for this design. We delay each channel by different times, ranging from 0 to 500 milliseconds, maybe a bit longer. It can actually go a little bit longer based on if you're willing to experiment. Each channel gets their audio sample shuffled around for randomization and are sent to a Hadamard mixing matrix to mix all of them together. From there, the audio is sent to a feedback delay network. A network that, while sending audio to the output, delays each channel again by different delay times, these times being way longer, being even full seconds long, and are once again mixed before being sent back to the input at a lower amount of energy, creating repetitions in our output and creating repetitions for our repetitions that slowly fade away. We also mix back down to the original number of channels in the input for the output as well. I forgot to say that. And with all of this together, we get a sound like which can sound a little bit grating, I do admit. Reverbs are usually a bit low end heavy and doesn't have that much high frequency content going on, so adding on a low pass filter is definitely something to look forward to really finish this thing off. But still, with a little help from the author himself, I was able to build this as a pre-year 1 undergrad while working a full-time job at the time in just about a month. Pretty cool if you do say so myself. If you want more information on how parameters can be added, you can check out the talk itself and the supporting article as well. If you also have any questions, you can always reach out to Gariant himself on the Audio Programmer Discord server. Just, remember that he is a human being, he has a whole life, so whenever he's able to get back to you, he'll get back to you, but just keep that in mind. I'll also be uploading walkthroughs on how I implemented the whole algorithm myself on my Patreon, as well as how to implement the different matrices. You can actually access that on my Patreon for free. You don't have to be a member for that. You might have to be a free member, but you don't have to pay anything, so you can just check that out on there as well. I just didn't feel like making it into a whole YouTube video, and so yeah, you can just figure it out there. As for the source code, just like my last video, it'll be made public once the next video goes up, but if you can't wait that long, you can just check out my Patreon as well. It'll all be on there as well, support the channel, please. That being said, sorry for the late video and the switch up on the topic. We're gonna have to do a little bit more work on what I was originally gonna plan to upload, but yeah. Thank you for watching.